Hello, good morning everyone. So today we are going to continue our discussion related to Bayes learning, and we are going to cover one of the important algorithms, and that is known as Bayes optimal classifier. So before proceeding with Bayes optimal classifier, let us have a recap. In the last class, we had a discussion related to Bayes theorem, and we have seen how to use Bayes theorem for machine learning. So we have defined Bayes theorem like finding out the probability of H given D equal to probability of D given H into probability of H divided by probability of D. So this is our Bayes rule, wherein we are considering hypothesis probability of hypothesis H, probability of the training data D, right, and two conditional probabilities. So here, as we have seen, what is this probability of D given H? Probability of D given H is the probability of observing data given some hypothesis H. So this is probability of observing data given some hypothesis. Right? What is this probability of H? Probability of H is the prior probability. Probability of H is the prior probability or the initial probability of hypothesis H. So this probability is before observing data. Right? And what is probability of D? It is the prior probability of training data. So here we are assuming, or while computing this prior probability of training data, there is no knowledge about the hypothesis, right? So if we know these three quantities, it is possible to find out probability of the hypothesis given the training data, right? So this is what we wanted to compute. And this is how we applied Bayes theorem for finding out the hypothesis given some training data. Further, what we did, by making use of this Bayes theorem, we wanted to come up with a maximally probable hypothesis. Right? So we have came across the concept of a maximum a posteriori hypothesis, and we denoted this maximum a posteriori hypothesis as HMAP. Right? And how we define this HMAP? We define this HMAP as Argmax H that belongs to capital H, probability of D given H into probability of H. So by making use of this expression, it is possible for us to compute the maximally probable hypothesis. Further, we simplified this expression of HMAP we came up with HML. What is this HML? HML is the likelihood, maximum likelihood hypothesis. This is maximum likelihood hypothesis. And to come up with this maximum likelihood hypothesis, we assumed that all hypotheses in hypothesis space are equally likely. That means probability hypothesis HI is same as probability of hypothesis HJ for all HIs in our hypothesis space capital H, right? So we come up with HML, that is the maximum likelihood hypothesis, as R max, H belongs to capital H, probability of D given H, right? So in the last class, we have covered all those concepts and we have also gone through one example. Now, today we are going to discuss Bayes optimal classifier. So far, we have considered the most important question. What is the most probable hypothesis given the training data? So far, what we did, we tried to find the answer for the question, what is the most probable hypothesis given the training data? This is the hypothesis that needs to be used for classification, right? In fact, the question that is of most significance is slightly different, which is closely related to the earlier question. We are talking about Bayes optimal classifier, and so far we tried to answer the question, that is, what is the most probable hypothesis? Most probable hypothesis given the training data. So, as I stated, we are interested in finding out question, what is the most probable classification of the new instance given the training data? So what is the difference in these two? Anybody who can distinguish between these two questions? The first question was, what is the most probable hypothesis given training data? And the second question that we are arising here is, what is the most probable classification of the new instance given the training data? And what is the most probable classification? See, whenever we say that the most probable hypothesis, see, for example, recall back, right? That suppose we are having this two-dimensional space, okay, and we are having some instances. And let us assume that these instances belong to two different classes. So, what we mean by hypothesis? The hypothesis may be a decision boundary like this, or we may have another decision boundary like this, right? So, we are having various hypotheses in our hypothesis space. So, what earlier we were trying to find is, which is the most probable hypothesis, which is the most probable hypothesis, meaning this is my H1 and this is my H2 and so on. But select this H1 or other to select this H2 and so on. So we were trying to find out the probability of hypothesis H1 given D, probability of H2 given D and so on. And whichever is the highest probability, that hypothesis we were picking up. Right? This is what we want actually is what is the most probable classification of the new instance. What does this mean? If I am having many hypotheses and if every hypothesis is classifying the instance in a particular class. Suppose we are having one more hypothesis like this. And let us assume that this is H3. Okay. Now, if I look at this H1, then this particular instance will be classified, say, as positive. Suppose red is positive and this green is negative class. Okay. So, if I pick this hypothesis H1, this instance will be classified as positive. If I pick this H2, once again, this instance will be classified as positive. Right? If I pick this instance H3, then also this will be classified as positive. But now, let us assume that we want to classify this particular instance. Now, if I want to classify this instance, what will happen? If I select this H1 hypothesis, then this instance will be classified as negative. If I pick this H2, then this instance will be classified as negative. But if I pick this H3, this instance will be classified as positive, even though it is negative. Right? So depending on whichever is the hypothesis that we are selecting, the test sample is being classified. And it is not enough that we should consider only most probable hypothesis, but it is better if we try to find out the most probable new instance given the training data. I'm going to illustrate this with example as well. Right? So, if I want to answer this question, one may say that use the training data, learn our hypothesis H map, right? And this H map will provide us the most probable hypothesis. But as I stated, we do not interested in only finding out the most probable hypothesis, but we want to find out the most probable classification of the new instance, and based on that we want to pick the hypothesis, right? So if we are using the earlier concept that we have learned, and if we try to find out H map, this is not the most probable classification, though it is giving us most probable hypothesis. So this is giving us most probable hypothesis, but it is not giving us most probable classification. So let us see with example what we mean by that. So for this, let us go through one example. Suppose we are having one hypothesis space H, and this hypothesis space H includes three hypotheses H1, H2 and H. Okay. Now let us assume that we have computed these values of H map. So posterior probabilities given the training data are already been computed. So we have probabilities with us. So probability of hypothesis H1 given data D is 0.4. Probability of H2 given D is 0.3. And probability of H3 given D is also 0.3. So this is the data that we have. Now, please tell me, what are those probabilities? These are the probabilities, those we have computed for all hypotheses, those belong to our hypothesis space. Right? Now, according to our expression for H map, what we are going to do? We are going to pick a hypothesis that is giving us the maximum probability. Do you agree with me? Yes? What we are having? We are having the probabilities of all the hypotheses given data D. Right? And by making use of the earlier concept of finding out the maximum a posteriori hypothesis H max, what we would like to do? We would like to find out, or we would like to select the hypothesis that is providing us the maximum probability. And that is the hypothesis that we say it is most probable. Do you agree with me? Yes. Is there any doubt so far? Please understand the concept. It is really very important. Are you able to understand?
Could you explain again?
So, have you understood what is the difference in most probable hypothesis and most probable classification? Yes
Not
or
exactly.
no?
Not exactly.
Okay, so let me once again repeat. See, what we are trying to do is, earlier, we were trying to find out the most probable hypothesis. So what do you mean by most probable hypothesis? We try to find out the probabilities for every hypothesis in our hypothesis space. So if I'm having 3 hypotheses in my hypothesis space, I'm trying to find out all these probabilities. Right? And we were picking up the hypothesis that is giving us the maximum probability. Right? And we the most probable hypothesis, H map. Right? So henceforth, whenever there is any test sample that comes in, we'll be making use of the H map, that is the selected hypothesis, and we will try to classify the sample. Right? That is what we learned earlier. But now the question is whether it is enough to have the most probable hypothesis, or rather we should go for the most probable classification of the new instance. What does this mean? This means that if I am having many hypotheses in my hypothesis space, those are actually for classifying my data. Suppose we are having this data set available with us. Okay? And we want to come up with a decision boundary. So this decision boundary is nothing but the hypothesis. Right? So I may come up with this hypothesis. I may come up with this hypothesis. Right? I may come up with this hypothesis. This is H2 and this is H3. Okay, so if I contain H1, then towards this side I'm having positive class. This side hypothesis I'm having negative class. Are you getting me? Yes?
Yes, ma'am.
Are you getting me?
Yes, ma'am.
Now, let us assume that we are having this new sample, test sample. Right? So this is my test sample. And I want to find out the class of this sample. If I make use of this hypothesis H1, then what would be the class for this? Towards this side of H1, I am having positive class, and towards this side of H1, I am having negative. So if I want to classify this sample using H1, what would be the class? Yes, I'm picking up this H1. I'm using this H1, this hypothesis, and I want to classify this particular test sample. So what would be the class for this sample, whether it is positive or negative? We are using this H1. Am I asking you a very difficult question?
Negative.
It is negative. Why? Because towards this we are having positive class, and towards this side we are having negative class. So H1 will classify this sample as negative. Is that correct? Now,
Yes.
let us consider now this H2. So for this H2, we may say that towards this side is positive class, and towards this side negative class. So if we are considering this hypothesis H2, what would be the class for this test sample with respect to H2? Yes?
Positive.
With respect to H2, it would be positive, right? H2 will classify the same sample as positive. Now, let us talk about this H3 now. So if I have H3, towards this we are having positive class, and towards this we are having negative class. Right? Now, same test sample, if we try to classify using H3, then once again it would be classified as negative. Do you agree with me?
Yes, ma'am.
Yes?
Yes.
Fine. So, if I am having many such hypotheses in my hypothesis space, every hypothesis may result in different class level. May result, not necessarily always, but it may happen that every hypothesis is giving me some and that be uniform. Okay, so what we are proposing is, instead of selecting the most probable hypothesis and only rely on that hypothesis, why not to consider all the hypotheses together? Right? So once again I am repeating, instead of relying only the most probable hypothesis, why not to consider the contribution of all the hypotheses while predicting the class of the sample? Right? So that is what we are trying to understand. Is it possible? And if yes, how? Right? So I am having here one example to illustrate this. Are you able to understand now?
Yes, ma'am.
Yes? May I proceed?
Yes, ma'am.
May I? Okay. So we are once again assuming that we are having three hypotheses in our space, and these hypotheses are denoted as H2 and H3. Now, we have computed the probabilities of all those hypotheses. Okay, so probability of H1 given D we know, probability of H2 given D we know, and probability of H3 given D also is known. According to our math hypothesis, what we are going to do? We are going to select the hypothesis that is giving us the maximum probability. So that is the most probable hypothesis that we are going to pick up. So based on the earlier concept of HMAT, the most probable hypothesis that we are going to pick up is H1. Why? Because probability of H1 given D is 0.4. Probability of H2 given D is 0.3 and probability of H3 given D is also 0.3. So which is the highest probability? It is the probability of H1 given D. So we will say that this H1 is our math hypothesis. That is the maximum a posteriori hypothesis. And we are going to make use of this H1, right, for classification of the new instances. Now, let us assume that the new instance X is classified as positive by this H1. Okay, but negative by H2 and H3. I'll repeat what has happened now. We have done this H1, that is the most probable hypothesis. And now the new instance comes in and we classify that new instance X. So as the H1 is the most probable hypothesis, we are going to classify the new instance according to the H1. And let us assume that H1 is classifying the new instance as class positive. Okay, but the remaining two hypotheses H2 and H3, they are classifying the new instance as negative. Right, so similar is this case. So H1 is classifying the new instance as positive and H2 and H3 are classifying the same instance. Now, according to our theory of math hypothesis, as H1 is most probable hypothesis, the new instance X will be classified as positive. Why? Because H1 is classifying it as positive and H1 is our most probable hypothesis. So we should pick that. And according to H1, that instance X needs to be classified as positive. So we will declare class of the new sample as positive class. Right? But we consider all these three hypotheses that we are having. The probability that X is positive is 0.4 because only H1 has classified the test sample as positive. So probability that my test sample X is positive is 0.4. That is the probability of H1 given D. But the remaining two hypotheses are classifying the test sample as positive. So probability that the sample is negative is 0.3 plus 0.3, that is 0.6. Right? And this is what we are now inferring. The more probability, you can see here, we are not saying probability. Classification here is negative, not positive. Are you getting me? Yes?
Yes, sir.
Got it?
Yes,
Please
ma'am.
try to understand the concept. So instead of finding out only the most probable hypothesis, we are trying to find out the most probable classification considering all the hypotheses that we are having. Right? Now, we would like to, whatever we discussed so far, we would like to formulate it properly. Right? So, let's proceed with the formulation of base optimal. Classification instance is obtained by combining the predictions of all hypotheses. Okay, so the most probable classification of the new instance is obtained by combining the predictions of all hypotheses. So how to combine the predictions of all hypotheses? Simply, we'll be making use of all these posterior probabilities that we have, and we weigh the decision by these posterior probabilities of various hypotheses. So, we come up with this expression. So, what this expression is, probability of Vj given D is equal to summation over Hi belongs to capital H, that is our hypothesis space, probability of Vj given Hi into probability of Hi given D. So what is this Vj here? Vj is the possible value or the possible class. So Vj denotes the possible labels, instances. Then my Vj would be either positive class, class 1, or negative class, that is class 2. Right? So, what this expression indicates, probability of Vj given D is equal to summation over all the hypotheses in our hypothesis space. We are summing up how we are making use of two probabilities. First is probability of Vj given Hi and probability of Hi given D. So what is this probability of Vj given Hi? Vj is my class label, right? So what is the probability that we are getting this class label Vj given the hypothesis Hi? So for every hypothesis in our hypothesis space, we are having this probability. Probability of getting, say, class positive given hypothesis Hi, or probability of getting class as negative given the hypothesis Hi, multiplied with probability hypothesis Hi given data D. So this weighted sum, this is actually the weighted sum. So this weighted sum will provide us the probability of having a particular label given data D. Right? We are going to look at this with examples so that you can have better idea what we are trying to do. Okay? So, are you able to understand till this? Yes?
Yes. Yes.
The optimal classification of new instance is the value Vj. So Vj is the class label. So the optimal classification of the new instance is the value Vj, for which probability of Vj given D is maximum. I'll repeat. Now what we are trying to do? We are trying to find out the maximum probability of Vj given D. So the optimal classification of the new instance is the value Vj, that is the label, for which this probability of Vj given D is maximum, right? So here we are formally writing our Bayes optimal classification expression for Bayes optimal classification. So this expression is giving us this probability of Vj given D. So how probable is this particular class label given the data? Okay, so what we are trying to do is, if I am having two classes, say positive, I am computing the probability for class positive given data. I am going to compute the probability that class is negative given data. Are you getting me? What this probability of Vj given D implies? Vj is the class level, right? So we are trying to find out the probabilities considering all the hypotheses. Probabilities that the test sample is positive given data. We are trying to find out the probability that the test sample is negative given data. So if we are having two classes, we'll be having two probabilities. If we are having more than two classes, we'll be having more than two probabilities, one per class, right? So once we are having all those quantities, what we are going to do next is we are going to apply this argmax. So we are going to pick the label. We are going to classify the sample with class Vj for which this probability is maximum, right? So if the probability for positive class is maximum, then we will declare the class of the test sample as positive. If the probability for negative class is maximum for the test sample, then we are going to declare that class of test sample as negative, right? So let me give you one example. Suppose our set V is having two classes, positive and negative, right? So this is my V1 and this is my V2. So we are having two possible class labels, positive and negative, right? And these two class label comprises this set V. Let us assume that we are having three hypotheses, H1, H2 and H3. So we know these quantities. So let us try to interpret this data. So probability of H1 given D is 0.4. Probability of H1 given D is 0.4. Probability of H2 given D is 0.3 and probability of H3 given D is also 0.3. Now, if I am using this hypothesis H1, then probability that I am having negative class given H1 is 0 and probability that I am getting positive class given hypothesis H1 is 1. Similarly, the probability for negative given H2 is 1, probability of positive given H2 is 0, and similar is the case for hypothesis H3. So this is the data that is available with us. So by making use of now Bayes optimal classification, we would like to classify the test sample. So if we want to classify the test sample, we are computing this quantity, right? So how we are going to compute this quantity? We are going to compute this quantity for all hypotheses. So having the summation for all the hypotheses. So what our formula says, it is summation over Hi belongs to H. So we are having three hypotheses. So how we are going to compute this? See, let us assume that our Vj is positive class. Our Vj is positive class. Okay, so for positive class, what we are trying to do? Probability of positive given Hi. So obviously here we should have probability of positive given H1 into probability of H1 given D plus probability of positive given H2 into probability of H2 given D plus probability of positive given H3 into probability of H3 given D. As we are having three hypotheses, we would like to compute this sum. So if we try to replace these quantities, those we are having, what is probability of H1 given D? It is 0.4. Right? What is probability of positive given H1? Positive given H1, it is 1. So this comes out to be 1 into plus probability of positive given H2, it is 0. So 0 into 0.3 plus 0 into 0.3. So it comes out to be 0.4. Are you getting me? Yes? Are you getting me? So what does this mean? This is probability of positive given D. Similarly, we are going to compute probability of negative given D. So see how we are going to compute this quantity. So this is probability negative given H1 into probability of H1 given D plus probability of negative given H2 into probability of H2 given D plus probability of negative given H3 into probability of H3 given D. So by substituting all those values, we know all those values, right? So what is probability of negative given H1? It is 0. So 0 into H1 given D is 0.4. So what about this? Probability of negative given H2 is 1 into 0.3. And here it is 1 into 0.3. So this summation comes out to be 0.6. So probability, considering all the hypotheses, the weighted sum, probability that my sample belongs to class positive given data D is 0.4 and probability that my sample belongs to class negative given data D is 0.6. Right? Now, what we want, we have computed these quantities for positive class and negative class. So we would like to pick the class for which the probability of this quantity is maximum. This quantity is maximum. Right? So we are having two quantities, 0.4 and 0.6. So which is the maximum quantity? This 0.6. So we need to pick the VJ. Of the test sample. Right? So here we are considering all the hypotheses in the hypothesis space and we are coming with the most probable classification instead of coming up with most probable hypothesis. Right? If you have any doubt, please let me know. Yes? Is there any doubt?
No, ma'am.
Understood the concept of Bayes optimal classifier?
Yes, ma'am.
Please try to understand all the expressions. The expressions are very simple as far as the interpretation is considered. If you know the notations, it would be very easy to interpret those expressions. It is not difficult. Right? So please concentrate and try to once again go through these concepts. Okay? So in the next now, after going through the Bayes optimal classifier, let us discuss about one more classifier, and that is known as Gibbs classifier. So, whenever we are making use of Bayes optimal classifier, it provides us best results, optimal results. But whenever the number of hypotheses or hypothesis space is very large, finding out the class of the sample by making use of Bayes optimal classifier can be expensive, because in Bayes optimal classifier we are trying to find out the probabilities for each and every hypothesis, and then we are coming up with the optimal class, right? Now, in Gibbs algorithm, we are trying to do the same thing, that is, we are trying to classify the sample. We can treat this as an alternative method for Bayes optimal classifier, but it is less optimal method. So Bayes optimal classifier is actually providing us the best results, but due to the computational overheads, if the hypothesis space is very big, we may come up with, or we may go with, this Gibbs algorithm, which is less optimal than the Bayes optimal classifier. Let us list out the steps in Gibbs algorithm. So choose one hypothesis at random according to the probability of H given D, and then use this hypothesis to classify the new instance. Right? So simply we are randomly picking up the hypothesis, and then we are making use of this hypothesis to classify the new instance. And the surprising fact that we can observe is the error that has been obtained by Gibbs algorithm is no worse than twice the error that we get by making use of Bayes optimal classifier. So please see this. This is the error obtained by making use of Bayes optimal classifier, and this error gives us the error obtained by Gibbs classifier. So surprisingly, even though we are randomly picking out the hypothesis, the surprising fact that we may observe in experimentation is the expected misclassification error making use of Gibbs algorithm is no worse than twice the Bayes optimal classifier. What does this mean? See, for example, if my Bayes optimal classifier is giving me the error, say 3%, misclassification error, say 3%, then the Gibbs algorithm will give me the error which is less than or equal to twice that error. So it is less than equal to 6%. So even though we may consider 6% error, that can be acceptable, right? And this is the simple modification in Bayes optimal classifier, which is known as Gibbs classifier, and surprisingly, it is giving us the results those can be accepted, right? And the computational overhead is also minimum. Okay. So with this, let us conclude today's session. Thank you.